So as you can see, I have already written the force diagram and its solution and answer for part A. So we can treat blocks A and B as combined system, in which case we have the force diagram of a force friction to the right, a normal force upwards, a force being pulled onto the left, and the weight force downward. Doing Newton's second law on the y direction, which we know is equals to 0, implies that N is equal to the weight, which is equal to 4.n newtons. Remember, this is the combined block system, so you have to solve for two weights. This means that Fk, the friction force, is mu Kn times the normal force, which is equals to 1.44 newtons after multiplying 0.3 and 4.8. Now we're doing Newton's second law in the x direction, which means it will give us 0 again, because these blocks are not accelerating. There may be constant velocity, which means that force we apply is equal to the friction force, which is equivalent to 1.44 newtons. So that's the answer for part A. So as you can see, I have already written down the solution and the force diagram, in order for me not to complicate talking while writing. So it would help if we draw the force diagram for block B. The force diagram is kind of complicated. As you can see, there's a normal force going up. There is a friction force. There's another friction force between the ground and block B. The reason why there is two friction force is one is responsible between A and B, and the other between B and the ground. There's also a weight force of block B, and there's also a normal force from block A being put down in block B. There is also a force that will apply to the left. Now, for block A, as you can see, the force diagram is much simpler. We are going to have the normal force just due to the weight of block A upwards. We have a tension and rope to the right. We have the weight to block A downwards, and friction to the left. Now the friction here is the friction between A and B. So they form a Newton's third law of pair. So FKB and FKA are actually opposite in direction. So instead of saying the vectors are equivalent, rather they are opposite in direction. So instead of saying the vectors are equivalent, we are going to take the absolute value and say that their magnitude are equivalent. So in NA is equivalent to NB. For the same reason, they form a Newton's third law of pair, and thus are equivalent in magnitude. Now, we're going to apply Newton's second law in the y direction. We're going to apply it for block A. And that implies that NA is equivalent to weight of A, which is equals to 1.2 Newton. This implies that FKA in the friction force mu KNA is FKA in the friction force is equivalent to mu KNA, and plugging the values 0.3 and 1.2 here, we will get 0.36 Newton. For that friction, again, this implies that F of KB is equal to 0.36 Newton, since they form Newton's third law of pair. Now, moving on, Newton's second law in the x direction, here in the x direction for A, here, Newton's second law in the x direction for A gives the tension to FKA. And we just found out that FKA was 0.36 newtons. The tension is also known I was wrong again. FKA was, so we just found out that FK is 0.36 newtons. So the tension is also 0.36. Now, we're going to apply Newton's second law again, except we're going to apply it to block B and do it in the x direction. So for B, this time, it gives the force that we apply is equal to this friction force, as you can see. So, my bad. So for B, this time, this gives the force that we apply is equal to this friction force plus this friction force, where we already calculated what those friction force are. These friction forces are 0.36 plus 1.44, which will then get 1.18 newtons. So, since we're done with the problem number 1, we're going to the next problem, which is 2 point charges Q1 and Q2 are held in a plate 4 cm apart. Another point charge Q is equivalent to negative 1.75 mu coulomb of mass, which has a mass of 5 grams, is stationarily located 3 centimeters from each of these charges and released from rest. You observe that the initial acceleration of Q is 3.34 meter per second squared upward, parallel to the line connecting the 2 point charges. Find QA and Q2. So, let's get it. So before we start the problem, we always draw a free body diagram labeling everything so that we would know what we're looking and what to find. So we're going to have a radius from Q1 to Q. So let's say radius from Q1 to Q, let's call it R1. We're going to convert centimeters to meters. So we're going to have, instead of 3 centimeters, we're going to have 0.03 meters. same as Q2 to Q, which is R2. We going and for the next one, we're gonna call this R1 and 2 because it's from Q1 and Q2 to Q. So, we're gonna call this R1 and 2 because it's from Q1 to Q2. So, we're going to get 0.045 meters. And we know that the charge on Q is negative 1.75 mu coulombs and has a mass equal to 5 grams. And we need to change that grams into kilograms. So we're going to get 0.005 kilograms. And the acceleration of Q is 324 meter per second squared. So we're lacking, or we need to find Q1 and Q2. So you might wonder why there is a positive and a negative sign there, but I'll explain it later. So we need to evaluate this free body diagram, and the good thing to start with would be recognizing whether Q1 is positive or negative, if Q2 is positive or negative, and identify the direction of the forces and electric field. And so first, for the acceleration, which is connected with the force, because force is equals to mass times acceleration. So acceleration on Q is straight upward. So the forces due to Q1 and Q2, because Q1 and Q2, which is this one, is parallel. Is parallel. So again, force is equivalent to mass times acceleration. So the acceleration on Q is straight upward. So the forces due to Q1 and Q2, because it's parallel like Q1 and Q2, see, as you can see, so Q1 and Q2 must equal each other, because if they aren't, then this wouldn't have a 90-degree angle. First off, Q1 and Q2, because of parallel acceleration, and after evaluating the diagram, this tells us that since the acceleration is going upward, so that means Q1 is positive. So that's the reason why I put plus on Q1. So, which means Q2 is negative. So since we know that the acceleration of Q, based on Newton's second law, gives us the magnitude of the force on it, we can then add up the force components, and the force is equal the force of Q, which is what you can see here. FQ on the Q1 cosine theta plus the force Q on the Q2 cosine theta. If we add them, we will have 2FQ sub Q1 cosine theta, or Q2, your choice. You can use either because, as I said, Q1 and Q2 are equal but has different sign. So after getting this solution, and now we know that the force on Q is going to equal 1 over 4 pi epsilon naught q1 over r squared. And it would be the same for q2. We also know that force is equals to mass times acceleration. So we're going using this equation for force is equals to mass times acceleration. Since we have the mass here and its acceleration, so we're going to solve for it. So 0.005 kilograms times 324 meter per second squared would result to 1.62 newtons. And now we want to add the force components and calling theta the angle between the line connecting Q1 and Q2. So that's the reason why I was able to put this line. And the line connecting Q1 and Q, so FQ Q sub 1 cosine plus, that's the reason why I resolved to this equation. FQ Q sub 1 cosine plus FQ Q sub 2 cosine theta. So it will lead us back to what we had earlier, which is this one. So we will have the same output. So again, I had some mistakes, but like I said, it will lead us back to what we had earlier, which is 2FQ Q sub 1, and that for force, we're going to have force over 2 cosine theta. Having this equation, now we can get, having this equation, and we have this, having this equation, we can start getting the answer for these equations. And with that, our force is 1.62 newtons over 2 times, which is the parenthesis 4, we're going to calculate cosine theta. So we're going to take a look at the free body diagram, which is here. So we're looking for cosine. So we're gonna have the distance from here to here. So given the line, and we're going on, and we need the half of it because of this line, we're going to divide 4.50 centimeters by 2, which will have 2.25 centimeters, and then divide by the hypotenuse there. So you're gonna have you're going to have 3 centimeters. You're going to have 2.25 and 3 centimeters. And if you calculate this, you're going to achieve 1.08 newtons. And now we're going to find the charges by solving for Q1. Using the Coulomb's law and the fact that Q1 and Q2 have equal magnitude but opposite signs, so we found the force Q1 and Q2, F, which is, where was it? FQ Q sub 1 is equivalent to 1. So we're going to use this equation here. So 1 over 4 pi epsilon naught multiplied by the magnitude of q times q1 over r squared. And we're going to rearrange it. So I'm just gonna make this 1 over pi epsilon naught is just gonna be k, so that it won't be that complicated. So we're gonna rearrange it to r squared times f q sub 1 over k and the magnitude of q. So since we have this, we have the numerical value of this this function, so we're going to substitute it. So first off, 0.03 meters squared times 1.08 Newton, my bad, over 8.99 times 10 raised to the power of 9 Newton times meter squared per coulomb squared times 1.75 times 10 raised to the power of negative 6 coulomb, which will result to 6.17 times 6.17 times 10 raised to the power of negative 8 coulombs. So as I've said earlier, Q1 and Q2 are equal but has the same signs. So as you can see here, Q2 is equals to negative Q1, which therefore if we change the sign of Q1, we will have negative 6.17 times 10 raised to the power of negative 8 coulombs. And that's how you solve the problem number 2. That's all.